So in part B of this question, we're given that we place a positive point charge at point C, so a plus Q, and we apply an external force and we move it from C to E to D to A. And we have this bar showing the work done to move it from C to E. And we need to represent the work done from E to D and from D to A with two bars. So if we go from E to D, what we see that in fact this is in an equipotential surface. So if we would use the formula that the work is the charge times the change in potential, on the equipotential surface, the change in potential is obviously zero. Therefore, this bar will be zero. However, if we move from D to A, we go from D, which is at 0 volts, to A, which is minus 10 volts. So we need to draw this in the correct ratio as from C to E. So C is at a minus 20 volt line, and E is again at a 0 volt line. So what we see is that we have 3 units that correspond from C to E for 20 volts. And so what we have for D to A is a 10 volt difference. Therefore, this will be 1.5 units. So we can do it in ratio. It's going to be exactly half the work. Therefore, we will draw a bar which is 1/2 of a rho. And in part 2, we need to calculate the approximate magnitude of the x component of the electric field at point B. So what we can do is approximate this as two plates being over here, this one being at minus 10 volts, this one being at minus 20 volts. And what we know is that the electric field is the potential gradient. So the electric field in the y component will be dV over dy, technically negative. So if we consider the distance between these two plates, we're given that one unit is 0.4. So we see that this will be approximately 1.4 meters, in which it changes 10 volts. So this will be 10 over 1.4, which will give us an electric field strength of 7.1 volts per meter.